Welcome back, math friends. This is AP Calculus section 5.5 notes, and this covers days 1, 2, and 3 of bookwork. So in order to use the evaluation theorem, which we've recently learned about, we have to be able to integrate many different types of functions. And we have lots of familiar integral rules, basically the reverse processes of our differentiation rules. But some functions do not follow any of the rules we know, so we need a new method for integrating these types of functions. And so we have an example here that's going to walk us through this process using the substitution rule. So we are trying to integrate the function 2x times the square root of 1 plus x squared dx. Now this is a function that's not easily integrated using the rules we know. So we're going to introduce this new idea called the substitution rule. And the substitution rule says that if we let u be g of x, part of our function, and if u equals g of x is a differentiable function whose range is an interval I, and f is continuous on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. Now that's a lot of fancy talk right there, but what I want you to notice when you look at that integral there in the bottom of the substitution rule box, notice that f at g of x times g prime of x. That looks an awful lot like the chain rule, doesn't it? And that if we are taking the integral of that, that gives us back the integral of f of u du. So in the cloud, it says, note that the substitution rule involves the chain rule. In some ways, it is like the inverse process of the chain rule because we are integrating instead of differentiating. So one thing that I want you to be thinking about as you do these problems that involve the substitution rule is whatever you are making your u, the derivative of that function should be somewhere within what's remaining in your function. Minus or, without considering any constant terms because those don't affect integration, or any coefficients, excuse me, because those do not affect integration. And again, I think you'll see what we mean as we practice some of these problems. We go through it and I will point it out to you as it occurs. So first of all, how does the substitution rule work? The first thing that you have to do is you have to select part of your function that is going to be called your u. And ideally, the derivative of u should also be part of the function. This is what I was just saying a moment ago. Without concerning yourselves with, and again, this shouldn't say constant term, this should say coefficients. Because these can be put in front of the integral if they are not part of the given integrand. And it says, note, deciding which part of the function should be u is the most challenging part of the process. And sometimes you need to try more than one thing before you get it to work. So just keep in mind, a lot of these problems, it takes more than one try to get it right. So don't give up, just erase and try something else. Okay, so for our integral, 2x times the square root of 1 plus x squared dx, we're going to let u equal 1 plus x squared. So now if I were to take the derivative of that, then du dx, the derivative of u with respect to x, well, the derivative of 1 would be 0, and the derivative of x squared would be 2x, right? And so then if I were to solve this for du, then I would get that du is equal to 2x times dx. Well, if I look at my original integral, if I let what's under the square root, which is 1 plus x squared, be my u, then that 2x dx would be equal to my du. So that works out well. So then step number 2 is we're going to rewrite the integral in terms of u. So this part, the square root of 1 plus x squared, well, if I let 1 plus x squared be u, then this part is going to be u to the, and I'm just going to write the square root as the 1/2 power, or the square root of u, it doesn't matter. And then the 2x dx we already established is our du, right? So that's how we get the integral of the square root of u du. And now our job is to integrate. So when we integrate u to the 1/2 power, remember, we are adding 1 to the exponent, so 1/2 plus 1 would be 3/2, but then we have to multiply in front by the reciprocal of our exponent to undo it. So it would be 2/3 u to the 3/2. And then, of course, we have to add our constant term plus c, right? Because we don't have any limits of integration here. And then after we do the integration, we would plug our u back in. And again, our u is the 1 plus x squared. So our final answer there is in this blue box, 2/3 times 1 plus x squared quantity to the 3/2 power plus c. And of course, you can always check your solution by differentiating. And if you do that, you should arrive back at your original function. And I want to remind you that if we were to differentiate what we just got, that thing that I just outlined in the blue box, that would require the chain rule, because we would differentiate the outer at the inner times the derivative of the inner. And I showed that work below here. The derivative with respect to x of 2/3 times the quantity 1 plus x squared to the 3/2 plus c. You bring down the 3/2. 3/2 times 2/3 makes 1. You still have the 1 plus x squared, but now 3/2 becomes 1/2, and then you have to multiply by the derivative of 1 plus x squared, which is 2x. So we end up with the function that we started with, which was 2x times the square root of 1 plus x squared. So that is, in a nutshell, how the substitution rule works. So let's begin by trying another example here. Example 1 says, evaluate the integral by making the given substitution. So in this problem, I have told you what your u should be, okay? So we already know that if u is 2 plus x to the 4th, I'm just going to rewrite that, then my du dx, derivative of u with respect to x, is going to be equal to 4x cubed. And if I were to multiply both sides by dx, then I would get du is equal to 4x cubed dx. And again, I said don't worry about those coefficients, because coefficients can be pulled outside the integral. So since I don't have a 4 as part of my integral, I just have the x cubed and the dx, I could certainly divide by 4. So du divided by 4 would be equal to x cubed dx. All right, so now I can take this and I can come up here and I can rewrite this as, here my integral of, and I'm going to put the 2 plus x, 2 plus x to the 4th to the 5th power, and then I'm going to put the x cubed dx at the end. I'm just rearranging it. I'm not changing anything yet. And so now you can see the substitution that I'm about to do. My 2 plus x to the 4th, that's my u. So I'm going to have the integral of u to the 5th. And then my x cubed dx is going to be equal to du over 4. But again, I can bring that 4, or the 1/4, excuse me, because it's divided by 4. So I can bring the 1/4 in front of the integral. And I can write this as 1/4 times the integral of u to the 5th du. And so now when I actually integrate this, I am going to get, if I add an exponent to 5, it's going to become 6. So the 1/4 stays, okay? And then I'm going to have 1/6 u to the 6th plus c. Okay. And 1/4 times 1/6 is going to give me 1/24 u to the 6th plus c. And then, of course, my last step would be to substitute what u was equal to back into my parentheses. So I end up with 1/24, and then u was 2 plus x to the 4th, and that is to the 6th power plus c. And again, you can always check your answer by differentiation. If we differentiate this, we end up with the same function that we started with. Example 2 says evaluate the integral by making the given substitution. Again, in this case, we are told what u should be equal to. So if u is equal to cosine theta, then du dx, derivative of u with respect to x, Derivative of cosine is negative sine. So this is going to be equal to negative sine theta. And then again, if I look at what I have in my function and I kind of want to make it match what's there, right? And I'm sorry, this should be du d theta here, not du dx. My apologies. I've got the sine theta. I've got the d theta. So I want to multiply both sides by d theta, but then I want to divide by that negative sign. So I'm going to have du over negative 1 is equal to sine theta d theta, right? So then I have exactly what I want. So now I can rewrite this integral here as the integral of, and again, if u is cosine theta, it's just going to be u cubed. And then I'm going to have my du over negative 1, which I can certainly pull out and put in front of my integral, right? So then this is going to be equal to negative the integral of u cubed du. And then I can go ahead and I can integrate this now. So I would change my exponent to the fourth and multiply in front by 1/4. I still need my negative sign, don't forget that. And then I need my plus c. And then I can go ahead and I can substitute in what u was equal to, which I know was cosine theta. So my final answer is going to be negative 1/4 cosine theta to the 4th power plus c, which, as we know, we can always write those trig functions with the exponent inside. So 4th power theta plus c, like that. Cosine to the 4th of theta plus c. Either one of these is fine notation as far as I'm concerned because they mean the same thing. Example 3, we want to evaluate the indefinite integral, and this time they are not telling us what to let u equal. Well, it might be easier as if we think of this as the integral of 1 over 5 minus 3x times dx. Okay, so now you just have to start somewhere and go with it. In this case, I would say I'm going to let u, since we don't have anything else in our function besides this 5 minus 3x, and I know that the derivative of that would just be negative 3, which isn't an issue because, again, I could pull that out in front of the integral. I'm going to try letting u be 5 minus 3x. See what happens here. So let's let u equal 5 minus 3x. Then du dx, the derivative of u with respect to x, is just going to be negative 3, right? Because derivative of 5 is 0, derivative of negative 3x is negative 3. And then since I just want the dx part, then I could multiply both sides by dx and divide both sides by negative 3. So I would end up with du divided by negative 3 is equal to dx. Okay, so now I can rewrite this integral as the integral of 1 over u times du divided by negative 3. And dividing by negative 3 is the same as multiplying by negative 1/3. So I can bring that out in front of my integral. And now I just have the integral of negative 1/3, or negative 1/3 times the integral of 1 over u du. And so now I just have to integrate that. Well, hopefully you recognize 1 over u. The integral of that would be natural log u because the derivative of natural log is 1 over the stuff, right? So this is going to be equal to negative 1/3 times the natural log. We're going to use those absolute value bars, just saying that whatever is inside there has to stay positive, plus our c, because again, no limits of integration here, so we need that plus c all the time. And then finally, if we plug u back in, we end up with negative 1/3 natural log of the absolute value of 5 minus 3x plus our constant term c. Example 4, we have the integral of cosine x divided by sine squared x dx. And again, it's kind of a horse apiece here. Do we let u be sine or do we let u be cosine? Well, if I let u be cosine, the derivative of cosine is negative sine, but the problem is I have a sine squared in my function. So it might be best to let u be sine x, and then the derivative would be cos x, and I do have that cos x dx. So I think letting u be sine x is going to work out better. But again, sometimes you try something and it doesn't work, and then you just have to try something else. So in this case, again, I am going to say, let's let u equal sine x. Then du dx is going to be equal to, derivative of sine is cos x. And if I were to solve for du, then I would get du is going to be equal to cos x dx, which is that part of my function. Okay, so it seems like this is probably the way I want to go here. So now I am going to rewrite this integral. And again, I'm thinking of this as 1 over sine squared x times cos x dx. So this part right here, this is my du. And this 1 over sine squared, well, u is sine x, so this is just going to be 1 over u squared. So when I rewrite this, it's going to be the integral of 1 over u squared du. And 1 over u squared, if I bring it upstairs, I'm not doing any integrating yet, I'm just rewriting it as a polynomial. It's going to be u to the negative 2 du. So now when I integrate, remember I am adding 1 to my exponent, so it's going to become u to the negative 1 power. And then I have to undo that by multiplying by the reciprocal of negative 1, which is negative 1, right? And then I need my constant term c because I don't have any limits of integration. And u to the negative 1 power is 1 over u. So negative 1 over u, I can write it like that, plus c. And then my last step would be to plug back in what u is equal to. And u is equal to sine x, so negative 1 over sine x plus c. And I'm sure you recognize that 1 over sine, the reciprocal of sine is cosecant. So we could also write this, it's a fine answer, as negative 1 over sine x plus c, but this could also be written as negative cosecant x plus c. Either one of these would be a correct solution. Next, we have a few examples where we are looking at definite integrals instead of indefinite integrals. And so this changes our process a little bit when we're using the substitution rule, because if we are changing our integral to be in terms of u, then we can either leave it in terms of u and integrate it that way, but we have to change our limits of integration to be in terms of u, or we can switch it back to x and then leave our limits of integration in terms of x. And I know that that sounds a little bit confusing right now with words, but as I go through the problem, I will show you both ways and I will explain it, and then I think it will become clear. So in example 5, we want to evaluate the definite integral. We have the integral from 1 to 4 of e to the square root of x power divided by the square root of x dx. So hopefully it seems obvious that perhaps we should let u be the square root of x in this problem, since that's the exponent on the e, but then that's also appearing in the denominator of our function. At least it's a place to start. It's something to try, right? We can always back up the bus and try something else if it doesn't work, but it's a good place to start. So I am going to say let u equal the square root of x. Then my du dx, derivative of u with respect to x. Now remember, square root of x is x to the 1/2 power. So if I differentiate that, I'm going to get 1/2 x to the negative 1/2, right? Which, if I rewrite that in radical form, du dx is going to be equal to 1 over 2 square roots of x. So if you look at that, that gives us our square root of x that we want in the denominator. And we have that 2, but again, no big deal. A 2 in the denominator can be factored out as a 1/2 in front of my integral. That's not an issue. So what I'm going to do right now is I'm just going to rearrange this a little bit. I am going to multiply both sides by dx, and then I am also going to multiply both sides of the equation by 2. Okay, so when I do that, I'm going to end up with 2 du is equal to 1 over the square root of x times dx. Again, I just multiplied both sides by dx, and I multiplied both sides by 2. Okay, so now if I am looking at my given integral, and I am thinking of how I'm changing this to be in terms of u here, so I've got the integral of e to the square root of x power times 1 over the square root of x dx. I'm just rewriting it like that, spreading it out a little bit. So then the first part of my integral, right here, this will become e to the u, right? And then my 1 over the square root of x dx, this part right here is going to be represented by 2 du. And again, then I can just put that 2 in the front of my integral. So this is going to be equal to 2 times the integral of e to the u du. Now notice I dropped my limits of integration at this point, right? Because I just rewrote everything in terms of u and x are not the same thing. So at this point in time, my limits of integration here are not going to be from 1 to 4 if my function is in terms of u. Now I can go ahead and I can integrate this, okay? So if I were to integrate e to the u, I know the derivative of e to the u is e to the u, so the integral of e to the u is also going to be e to the u, right? So the integral here is just going to be equal to 2 times e to the u. But again, now we have to evaluate this based on our limits of integration. So here's where this problem gets more complicated because it's a definite integral. So let's make a little note here. Now we need to evaluate based on the limits of integration. Right? Because normally we would write this and we'd put that little bar here and then we'd put our limits of integration on the top and the bottom. And so there are 2 ways that we can evaluate this. One way is by leaving it in terms of u, and the other way is by changing it back to x. And I'm going to show you both, and I'm going to show you that you get the same answer either way. So you just have to pick the method that you prefer and go with it, okay? So our first option here is if we leave it in terms of u. So if we leave our integral in terms of u, remember in the beginning we said that u was equal to the square root of x, right? Well then the integral from 1 to 4 is going to be equal to the square root of 1, because that would be the value of x, up to the square root of 4, which would be equal to the integral from 1 to 2. So if that's the case, then my 2e to the u evaluated from 1 to 2 is going to be equal to 2e squared minus 2e to the first. Again, that's just the evaluation theorem here, right? And then if I factored out the 2e from both terms, then I would just have e minus 1. And I'm going to leave my answer like that. I'm going to leave it in terms of e. Remember, e is just a number, okay? So that's how we would evaluate this integral, by leaving it in terms of u. Now our second option is to change it back to x. So and if I change it back to x, that simply means that I substitute back in whatever we made u equal to. I substitute that back in. So in this case, my 2e to the u when I substitute it back in, becomes 2e to the square root of x, right? Because that's what u was equal to. And now my limits of integration were the ones from the original problem, which were in terms of x, so from 1 to 4. And so now if I evaluate this, I'm going to get 2e to the square root of 4 minus 2e to the square root of 1, which gives me 2e squared minus 2e to the first, which again, if I factor out that 2e, gives me 2e times e minus 1. Same answer that I got when I left it in terms of u. So I don't feel that one of these is more work than the other. I don't feel that one of these methods is easier than the other. I just wanted to point out that they're both valid ways to evaluate the integral once you have done the integration step. You just have to choose whether you prefer to leave it in terms of u and then change your limits of integration, or whether you are going to plug what u was equal to from the beginning of the problem back in and then leave your limits of integration in terms of x. Okay, those are your two options. Let's take a look at example 6, okay? And I want to point something out here. This integral is from 0 to a. So in this problem, a is a number, not a variable. It's just that we don't know what number it is. It's generic. It's a. It could be anything. So our function is x times the square root of a squared minus x squared. So again, I want to point out here, note a squared is just a constant term. So when we are differentiating and or integrating, it is in terms of x. A is not a variable, okay? So when I look at this, obviously what's under my square root would be a squared minus x squared. Again, a squared is a number. I mean, a could be 5, so it could be like 25 minus x squared. Well, the derivative of that is going to be negative 2x. And I like that because I have that x dx. Right? So I think I am going to let my u be represented by what's under my square root, which is a squared minus x squared. Then my du dx, derivative of u with respect to x, is going to be equal to, again, a squared. A is a constant. So a squared is also a constant. Derivative of that is 0. Negative x squared, derivative of that is going to be negative 2x. And so now, just like I always do, I can do some rearranging here. I can divide by negative 2, and I can multiply by dx to try to make it look like the remaining part of my function here with my x and my dx, right? So if I do that, I will have du divided by negative 2 is equal to x dx. So then I can rewrite my integral, and again, I'm not going to put any limits of integration on it yet. So the square root of a squared minus x squared, I'm going to put first, and then times x dx, I'm going to put second, and I'm just kind of showing what I'm substituting in here. So here, this a squared minus x squared is my u, so this part's just going to be the square root of u. And then here, my x dx is going to be represented by my du divided by negative 2. And then I can pull that division by negative 2 out in front of my integral, which would be a negative 1/2 in front of my integral. And then I have square root of u du. And if I want to leave it in terms of u, remember that, so I'm going to write a little note here, I will leave in terms of u. Okay, so then my limits of integration, if u is a squared minus x squared, okay, then whatever my x values are have to get plugged in for x. So my limits of integration are going to become from my lower limit of integration here is going to become a squared minus and the x value on my lower limit of integration was 0, so a squared minus 0 squared. And my upper limit of integration is going to be a squared minus, and there the value of x is a, so a squared minus a squared. Okay, so when I simplify that, this is going to be negative 1/2 times the integral. A squared minus 0 squared is going to be a squared from my lower limit of integration. A squared minus a squared is going to be 0 for my upper limit of integration. And then I have the square root of u du. So now I just have to integrate. The square root of u is u to the 1/2 power. I'm leaving everything in terms of u. I already made that decision right here, right? So that's why I changed my limits of integration to be in terms of u. So let's see, I will have my negative 1/2 in the front, and then the square root of u, remember that's u to the 1/2, right? So if I integrate that, I'm going to be adding 1 to 1/2, which is going to make it u to the 3/2 power. But then I have to multiply by the reciprocal, so I needed 2/3 in front to undo my 3/2. And I am evaluating this from a squared to 0. Well, I can simplify a little bit. Negative 1/2 times 2/3 is just going to be negative 1/3. So negative 1/3 u to the 3/2 power evaluated from a squared to 0. Okay? And so now when I actually plug in my 0 and I plug in my a squared, again, you go top first, minus, and then bottom second. So this is going to be negative 1/3 times 0 to the 3/2 power minus negative 1/3 times a squared to the 3/2 power. Well, 0 to any power is 0 times negative 1/3 is 0. And then I'm going to have minus a negative, which is chop chop, going to make a positive here. And then a squared to the 3/2 power, well, power to a power we multiply, 2 times 3/2 is just going to give me 3. So I end up with an answer of positive 1/3 a cubed. And that is the answer to my definite integral. Our last example here in this section has to do with integrals of symmetric functions. So before we actually do example 7, I wanted to take a moment and I wanted to draw a little picture of an even function and an odd function here on the right hand side of your paper so that you can visually see why, if f is even, then the integral from negative a to a of f of x dx is just double the value of the integral from 0 to a, and why, if f is odd, then the integral from negative a to a is going to be 0. Okay, so we're just going to sketch some pictures here. First, we're going to take a look at what the even function looks like. And so if I were just to sketch a little coordinate plane here, and a very basic even function might just be either a happy or a sad parabola. I will draw a sad parabola to illustrate what I'm talking about here. And so if this were my function and I were integrating it from, let's call this point negative a, and let's call this point positive a, right? So we have symmetry here over our y-axis. And if we were just integrating this function from negative a to a, then we would be looking at the area under the curve here and here, right? Well, hopefully you can see that the integral from negative a to a of f of x dx is just going to be 2 times the integral from 0 to a of f of x dx. Because here we have a positive area, and here we have a positive area, and those two areas are the same, so basically we just get double one of them, and that's our answer. Now what about if our function is odd? Because that looks a little bit different. So if we have an odd function, changes our picture slightly, and you know, a classic odd function would be either a cubic or a cube root or something like that. And so here's what looks like perhaps the cube root of x. And so in this case, if I say that This right here is negative a, and this right here is positive a, then I would be looking at this area and this area, right? And keep in mind that the area here on the left-hand side is going to be represented by a negative area, and the area here on the right-hand side is going to be represented by a positive area. I know that's a little bit hard to see, sorry. So here we are looking at the integral from negative a to a of f of x dx, basically canceling out, right? Because the area under the curve, or under the x-axis, and between the curve and the x-axis, and then the area above the x-axis, but between the x-axis and the curve, they're the same absolute value of the area, but one is negative because it's below, and one is positive because it's above, so they cancel each other out. Okay, so this integrals of symmetric functions here is just kind of interesting information. When you are working with a function that has symmetry, it might help you to simplify your integration process a little bit. And we are actually going to use the integral of symmetric functions in example 7 here to verify that f of x equals sine cubed x, or sine of the cube root of x, excuse me, is an odd function, and then use that fact to show that that integral from negative 2 to 3 of sine of the cube root of x dx has to live between 0 and 1. Okay, so we're going to do example 7 in 2 steps. The first step is we're going to verify that f of x is odd. And I apologize, you're going to need to write small here. I would start right below the function and use that space first, but we are going to need to use all of our space here to accomplish the problem, example 7. So the first step is going to be to verify that f of x is odd. And we are going to do so in the same way that we always determine if a function is even, odd, or neither. We substitute in negative x for x, and we simplify, and we see what we get, right? And the rule is that if f of x is odd, then f of negative x should be equal to the opposite of f of x for all x, okay? So if we are starting with the function f of x equals sine of the cube root of x, and I were to plug in negative x for x, it would look like this. And the cube root, we know the cube root of any odd value comes out, or excuse me, the cube root of any negative number is negative. For example, the cube root of negative 8 would be negative the cube root of 8, or negative 2, right? So we can simplify this and say that this is going to be equal to the sine of negative the cube root of x, and we know that the sine of negative x is equal to negative the sine of x. So if you look at that, what we notice is that f of negative x is equal to negative the sine of the cube root of x, which is the opposite of the function that we just started with, okay? So right here, we can do a little, right below there at the bottom, I ran out of room, but at the bottom I would write my little, therefore triangle of dots and say f of negative x is equal to negative f of x. Check, okay? So that's my verification that f of x is odd. So now the second thing that I want to do is use that fact to show that that integral from negative 2 to 3 of sine of the cube root of x dx has to live between 0 and 1. So for that, I'm going to need some more space here. So I am going to show that 0 is less than or equal to the integral from negative 2 to 3 of the sine of the cube root of x dx, which is less than or equal to 1. So essentially, this is asking us to do a proof here, okay? All right, so I'm going to start with the fact that I would like to use either the even and the odd integrals of symmetric functions that I just learned above. And so I am going to split this integral apart into two pieces because we know that the laws of integrals say that we can do that, right? We can break it apart into chunks along our x-axis. So here's what we know. All I'm going to do is I'm going to split this apart. I'm going to say that the integral from -2 to 3 of the sine of the cube root of x dx is going to be equal to the integral from -2 to 2, so there's the symmetry part of this, of the sine of the cube root of x dx plus the integral from 2 to 3 of the sine of the cube root of x dx. Okay, and right here, there's my odd function, right? The sine of the cube root of x is an odd function. So I can say right there that because sine of the cube root of x is odd, this integral equals 0. Okay, so I know that that part of it is going to be equal to 0. So the other thing is, well, what about that integral from 2 to 3 of the sine of the cube root of x dx? Okay, well, if you were to graph the sine of the cube root of x on your graphing paper and just look at it between x equals 2 and x equals 3, okay, along the x-axis. So I'm just going to make a tiny little sketch here. Here's my x-axis. Here's my y-axis. Oops. Can do a little better here. Okay, so x equals 1, x equals 2, x equals 3. And we are just concerning ourselves between x equals 2 and x equals 3 right now, because that's that. We already know that the integral from -2 to 2 is 0, so we're focused on the integral from 2 to 3, because that's really what we have to show is between 0 and 1, because we already know that the other part of our integral is equal to 0. So if I put a little line, a little vertical dashed line here between 2 and 3, I am just concerning myself with what's going on there. And I want to show that this integral's value has to be somewhere between 0 and 1. Okay, I have to show this. That's my job. Well, if I add to my graph on my graphing calculator the line y equals 1, y equals 1 is right here. Okay, and my graph on my graphing calculator, just the little piece, so I'm going to go ahead and I am going to pull that up so that we can see it. In my y1, I am going to put my function, which is sine of the cube root of x. And I'm under math here, I want to go to the cube root here. So sine of the cube root of x. And again, the window that I'm looking at here is just from x equals 2 to x equals 3. So I'm going to change my window from x equals 2 to x equals 3. Okay, and my x scale I'll just change to 1. And my y min I'm going to set at 0, and my y max I'm going to set at 1. Okay, so that's that line y equals 1 is going to be the top of my rectangle here, and I'm just going to take a look at this graph. So there is the function, the sine of the cube root of x, just between x equals 2 and x equals 3. So you can clearly see that it stays below y equals 1. And if you wanted to go to your y equals, and in y2 you wanted to put y equals 1, and then you wanted to go back to your window and change your y min, or leave your y min at 0, but maybe change your y max to 2 and regraph this, then you can see a little bit more clearly. Here is, again, my sine of the cube root of x. That's my blue graph. And after that finishes its graph, the horizontal line comes. There's my y equals 2, and you can see that the blue line stays below that horizontal line at y equals 1 the whole time, okay? So going back to this little picture that I'm making on my paper here, and again, I don't really care what's happening outside of x equals 2 and x equals 3. I just know that within those two green lines, my function looks something like this, right? And so the integral that I'm talking about is this area that lies below the curve and above the x-axis. So if this right here is y equals 0 and the purple line is y equals 1, I think we can safely say that that sine of the cube root of x has to be something that is a number less than 1, right? So here's what I'm going to call my step A when I write it down. I'm going to say A, start with 0 is less than or equal to sine of the cube root of x is less than or equal to 1, right? Because I just showed that. I just showed that that function lives between y equals 0 and y equals 1 on my graphing calculator. That was the picture that we just drew of that blue shaded region. And this is on the interval 2 to 3, right? Because that's the interval that we are, that we looked at, because we split our integral up into -2 to 2 and then 2 to 3. All right, so now our step B, I'm going to make a rainbow here. Our step B is we are going to integrate all terms from 2 to 3. Okay, so when I do that, I am going to have the integral from 2 to 3 of 0 dx is less than or equal to the integral from 2 to 3 of sine of the cube root of x dx is less than or equal to the integral from 2 to 3 of 1 dx. Okay, so I just integrated all terms from 2 to 3. Okay, now my next step is going to be to simplify this, because this part of my integral is just going to be 0, and this part of my integral is just going to be 1. So when I simplify it, I don't think you're going to see yellow, so I'll do this kind of turquoise color here. So when I simplify, I get 0 is less than or equal to the integral from 2 to 3 of sine of the cube root of x dx, which is less than or equal to, and the value of that integral is 1. Okay? And then my next step, I'll call it my step D, is that I have to add that symmetric integral, the -2 to 2 of sine of the cube root of x dx, which I know is equal to 0. I have to add that back into all sections because this is a proof, and I'm really supposed to show that the integral from -2 to 3 lives between, not just the integral from 2 to 3, right? So I just have to add that back into each section. So my step D is going to be add the symmetric integral from -2 to 2 of sine of the cube root of x dx to all 3 sections. Oops, all 3 sections. Okay, so when I do that, sorry, this is going to be a little smushed here. I'm going to have the integral from -2 to 2 of sine of the cube root of x dx plus 0 is equal to the integral from -2 to to 2 of sine of the cube root of x dx plus the integral from 2 to 3 of sine of the cube root of x dx is less than or equal to the integral from -2 to 2 of sine of the cube root of x dx plus 1. Sorry, I squished that a little bit. And then once again, I can simplify. So step E, we are going to simplify that because we know that that's our odd symmetric integral. That's equal to 0. So I end up with 0 plus 0 is, sorry, this was supposed to be a less than or equal to sign, is less than or equal to 0 plus the integral, because again, that's equal to 0 from 2 to 3 of sine of the cube root of x dx, which is less than or equal to, this part is 0 plus 1. And then finally F, which I will call my ta-da step. 0 plus 0 is 0, right? So this is sort of going to be my therefore. So 0 is less than or equal to the integral from 2 to 3 of sine of the cube root of x dx, which is less than or equal to, and 0 plus 1 is 1. So using the symmetrical properties of an odd integral, or the symmetric properties of a function that is odd, right? The integral is going to be 0. Using that, combined with the fact that we know that the area under the curve between what was left, so between 2 and 3, had to be less than 1, we trapped that in between 0 and 1. Then we added back in our symmetric integral and evaluated that as 0. And so basically we were able to show that the value of this integral from 2 to 3 has to live between 0 and 1.